Hello again everyone. Today we're going to have a look at the alcohols and carboxylic acids topic. I think that's what it's called. Yeah, so topic 2.7, alcohols and carboxylic acids. As with the previous topic, I'm just going to try and chat you through the different parts of the content, highlight key points, and then I'll set some work based on that. So first thing, there's 3 different types of alcohols. It's actually quite important that you can differentiate between the 3 different types. So you've got a primary alcohol, a secondary alcohol, and a tertiary alcohol. So primary alcohols, carbon with the OH. So the carbon with the OH is attached to one other carbon. So like that sort of setup. So ethanol would be an example of a primary alcohol. Secondary alcohol, the carbon with OH is attached to 2 other carbons. So there's the most simple version of a secondary alcohol. Add the hydrogens in, and then a tertiary alcohol would have the carbon with the OH attached to 3 other carbons. So the carbon with the OH is attached to 1, 2, 3 other carbons. So there would be the simplest version. So you will later in the topic learn a bit more about the significance of these. You'll learn about something called oxidation reactions, where it's impossible to oxidize a tertiary alcohol. You can oxidize a secondary alcohol, but only up to a certain point, and then a primary alcohol you can oxidize completely. So this topic starts out with you looking at how to make an alcohols, so production of alcohols, and mainly focused on how ethanol is made. So there's 2 ways. Let me go. There's 2 ways of making ethanol. You've got hydration as a technique, and you've also, so method 1 is hydration, and then you've got method 2, which is fermentation. So hydration uses ethene. So you take ethene, let's draw out displayed formula. So you take ethene like that, and an alkene, you add water to it as a gas, so water vapor to it, and under certain conditions, so under a high temperature or moderate temperature of 300 degrees Celsius, high pressure of 60 to 70 atmospheres, and using a phosphoric acid catalyst, so H3PO4 catalyst, this reaction happens, and you get ethanol being made as a product. Now, you may have already learnt about reversible reactions, you may not have. I'm just briefly going to talk about it here. So this is an example of a reversible reaction. So when the system is in equilibrium, you'll have the reactants converting to make products at the same rate as you'll have the products, in this case decomposing to make the reactants, and they'll be stable. Now these conditions are kind of like, or they are a compromise. So you'd expect higher temperature to mean faster rate of reaction, but they have to meet a compromise in order to get the maximum yield of products. The pressure, high pressure, is really just to get a high yield of products. So the higher the pressure, the better. The reason the pressure isn't higher, even higher than this, is that it costs a lot of money to get the pressure that high. So if they could make it higher without it costing much more, then it would be better, because 1, it would improve the yield. So high pressure, you got 2 moles of gas here, you got 1 mole of gas over this side. So high pressure would favour the equilibrium shifting to the right, and also high pressure increases the rate. Actually, the high temperature, because it's an exothermic process in the forward reaction, so because delta H is negative, the higher the temperature we use, actually the equilibrium shifts in favour of the left hand side. So in terms of yield, higher temperature actually decreases the yield, but if we lower the temperature too much, then the rate of reaction is too slow, and although we'll get a very high yield of the product, it'll take ages to actually finish the reaction, and so there's a compromise with 300 degrees Celsius. Catalyst, introducing a catalyst increases the rate of reaction, has no effect on the position of equilibrium, so it doesn't do anything to the yield, but it does increase the rate, so no-brainer in terms of introducing a catalyst there. Fermentation uses glucose, so you've got C6H12O6, which is sugar. You ferment it and it gives you your ethanol, so I'll draw chemical formula for that one, and carbon dioxide as your reaction. So this process of making the alcohol uses yeast as a catalyst. So a yeast catalyst again is added to get the reaction working, to increase the rate of the reaction. You use a temperature of about 35 degrees Celsius just to speed up the reaction, and also so that you can perform distillation of the material. So what happens is, as you heat up the material, using the yeast catalyst is going to break down and make you ethanol, and as you do the reaction you try and separate out the ethanol, so you'll have a setup that sort of looks like this. I'll draw it small down the bottom here. There will be your sugar with your yeast, and it'll be making alcohol, and what you do is you heat it up, and you heat it up so that the alcohol that gets made would evaporate and travel up through into a condenser. So this is my awfully drawn condenser, but hopefully you get the idea. Travel into a condenser where there'll be water coming in and going out. It'll cool it down and it'll travel as a liquid out through to the end. So the end in the container here will just have the alcohol being made. So the sugar and the yeast get heated up slightly, it'll be producing alcohol. We'll make sure the temperature is high enough to cause the alcohol to evaporate, and then it will travel across here and down and be condensed to give us alcohol or ethanol at the very end. Okay, so it's important to be able to compare these two processes, because we've got to decide which one to use, which one is better. So in terms of hydration, the ethene comes from crude oil. So it uses crude oil to source the ethene, which is non-renewable. So that's the bad thing about the hydration process. A good thing about it is all of the atoms in the reactants actually end up making the product that you want. So all of that stuff actually ends up making our product there. So we say it has 100% atom economy. So that's a good thing about it. This is a bad thing. This is a good thing. Another good thing about it is that it's very fast. So you can make the alcohol quickly, and it's a continuous process. And your product, so one other thing, is your product is pretty much pure. So you get a very pure product. You get pure ethanol being made. Maybe I'll come back to that in a second. So fermentation, good thing about it is it uses sugar as the reactant, which is a renewable source of energy. So you get sugar plants, you can just plant the plant and grow the sugar canes, and that will then provide you your reactant, so it's renewable, you can grow it over and over again, you're never going to run out, whereas the crude oil you will eventually run out. A bad thing is the atom economy. If you look at the atoms in the sugar, actually not all of them end up being used to make the ethanol. Some of them are used to make carbon dioxide, so the atom economy is less than 100%. So that's a negative aspect of this process. Another negative aspect is actually slow in comparison to the hydration process. So these conditions actually make this form of production very fast, whereas for fermentation, this form is very slow form of production. So another good thing about fermentation is because it is made using sugar, the time that the sugar plants spend growing, they will be photosynthesizing. So photosynthesis of the sugar plants actually the carbon dioxide that gets made in this process is offset or taken away, you can think of it as, by the time that the sugar plants spend photosynthesizing. So photosynthesis of sugar plants offset CO2 produced in the process. Okay, so that's how you can make alcohols. Now we're on to what you can do with them, so what reactions can you do. They actually make really good fuels, so when you burn the alcohols they release a lot of energy. So when we burn something, if I flip back to my original colour, so an alcohol, if you burn it in oxygen, it makes carbon dioxide and water. And actually, when we do it, it releases lots of energy. So it's a very exothermic process. You can use it in order to harness some energy. So an example where we might do this, let's pick an alcohol. So let's pick this alcohol, so 2-methyl or methyl propan-2-ol. If I was to burn it in oxygen, I'm going to get myself carbon dioxide and water. So those are always the products that you make when you're burning the alcohols. If I was trying to balance this equation, I'd first balance the carbons, so put a 4 in front of this for the 4 carbons. Then I do the hydrogens, so 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I put a 5 there, I've now got 10 hydrogens. And then I do the oxygens, so 5 oxygens plus 8 oxygens gives me 13. So there's 13 oxygens on this side in total. There's 1 there, so I need 12 more. So if I put a 6 there, now that equation is balanced. So that's reaction number 1, which is combustion. Second type of reaction is called dehydration. So think about, if you become dehydrated, you lose water. So at some point in this reaction, water is going to be lost. So if we pick, I might pick, what alcohol should we pick? Let's do butan-2-ol as an example of an alcohol. Like this. So you add, you have 2 options really. You can add concentrated phosphoric acid, or you can add concentrated sulfuric acid, so conc H3PO4, which is the phosphoric acid, or you could add conc H2SO4 as my dehydrating agent as well. These are used all over the place in order to remove water. So if you remember these as things that remove water, that might be quite helpful for you. So we're going to lose water. We're actually going to lose the OH here, and then we'll lose that one of the hydrogens on the neighbouring carbons, so either one of these two or one of these three. It's on one of the carbons that's neighbouring the carbon with the OH. So let's imagine I picked to lose that hydrogen. I'd end up with this as a product. Like that, so that's going to give me but-1ene. Let's imagine instead I actually I lost the OH still, but I lost this hydrogen, so on the opposite carbon now. 1, 2, 3, 4, you end up with but-2ene. So actually you get two products being made in this situation. So there's one thing that I forgot with this, to add as the other product. So if we're losing water, we need to add water as a side product onto these reactions. So I'd end up both of these being made if I was to perform this reaction. So it's not that there's two reactions going on, both of these things are being made. You don't need to worry about which one we make more of, just that we make both of those two as potential products. So the last type of reaction is the biggest one in the topic, which is called an oxidation reaction. So this is the last type of reaction for alcohols, not the last reaction in the topic. Oxidation reactions. So this is where the whole primary, secondary and tertiary alcohols come into play. So I'm going to draw one of each. We'll try and keep them the simple version. So let's do that as an example. So ethanol, let's do what am I doing? OH, let's do this as an example. And then let's do a tertiary alcohol as well. So like that as an example as well. So we've got a primary, secondary and a tertiary alcohol in each of these. Just add in the hydrogens. Okay, so ethanol, propan-2-ol and 2-methyl or methyl propan-2-ol as well. So primary, secondary and tertiary alcohols. In order to oxidize them, you have a choice. You can use potassium dichromate, so that's potassium dichromate, and it has to be acidified. So to acidify it, you usually use sulfuric acid. So aqueous potassium dichromate and aqueous H2SO4. That then, instead of writing all of that out in the equation, you just summarize it as O, which stands for oxidizing agent, something that adds oxygen. So in each of these we're going to use O as our oxidizing agent, something that adds oxygen. Now if potassium dichromate successfully oxidizes any of these, what will happen is it will have a colour change from orange into green. So if we get a successful reaction, this reagent is going to change from orange into green, and it will tell us that we've been successful. So first one, let's start with tertiary alcohol. If I try and oxidize it, there is nothing that happens. So no reaction, no matter how much I heat it up, no matter how hard I try, there's no reaction that happens. So tertiary alcohols, no reaction, no change. Secondary alcohols, you would add these things and you could reflux. So you'd need to reflux, which if you look back on a previous video I explained how that works. It involves heating it up but in a controlled manner. If we oxidize by reflux a secondary alcohol, what you end up making I'm just going to move the carbons around, you end up making a ketone. So that is what I make, so I end up making a ketone. It is a successful process, so potassium dichromate will have gone from orange here, it will be green over at the other side. So I'll have got myself a colour change, and the side product would be H2O. So where did the two hydrogens and the oxygen come from? This hydrogen is now missing, and that hydrogen is now missing. So you've got these two hydrogens, which is the H2, and the oxygen is the oxygen in there, so H2O. That's where that comes from. If I was going to try and oxidize this any more, so let's imagine for some strange reason I thought I could make a carboxylic acid out of this. If we try and draw that, so there's the carboxylic acid. Hopefully you can tell why that doesn't work. So if we look at this carbon here, it's got 1, 2, 3, 4, 5 bonds, so doesn't work. If we just put a cross through it to say that that doesn't work, we wouldn't be able to oxidize that further. So secondary alcohols, oxidize them using the oxidizing agent, reflux it, and you get a ketone, and it's impossible to make it go further. The primary alcohols, if I oxidize those, so one thing I can do is do what's called a mild oxidation. So I add these things, but I would distill it. So if I say mild oxidation, distill it, so perform distillation, what I'll end up making is an aldehyde. So there's my aldehyde being produced. And obviously I need to have H2O as a side product. Now if I choose to heat that up by a bit more, and I choose to reflux it, so more intense heating, that can oxidize further and actually produce a carboxylic acid. So if we do a mild oxidation on a primary alcohol, we get an aldehyde being produced through the oxidation. If we do a strong oxidation, so if we think of reflux as a strong oxidation, we can get it to go all the way through in order to produce a carboxylic acid. In terms of colour changes, if I do an oxidation, it will turn, the oxidizing agent will turn green. So going from here to here, it will go from orange to green, or if I go from here all the way to this side, it will go from orange to green as well. Now there is another oxidizing agent that you could use, or they could ask you about. It does exactly the same things, you represent it in exactly the same way. So it's potassium manganate, KMnO4. You'd have it in aqueous conditions. You'd make sure it's acidified, so usually by adding sulfuric acid. And that again could be acting as your oxidizing agent. So either of these two things will work. The only difference being that this reagent has a purple colour, so when it successfully oxidizes something, it goes from purple to being colourless.